Hello, my name is Nancy Sandler. I am a faculty at the Department of Physics and Astronomy at Ohio University, and I am here to guide you through a tutorial on strained graphene membranes that is part of Carbon Line Hagen, the online symposium on two-dimensional materials. So let's jump right into it. So the topics that I am going to cover in this tutorial are briefly described in this outline. First, I am going to review some basic facts about the graphene structure and the lattice model, and I will use those to motivate the description in terms of the tie binding and the low energy Dirac Hamiltonians. And I then will introduce the strain, and I will tell you the origin, or I will show you the origin of two of the most known players in the description of the deformed graphene membranes, which are known as the pseudo-gauge and the pseudo-magnetic fields. I will use them to show how a strain can confine electronic charges, and we can use it to waveguide electron dynamics, and with a look at potential applications, and we'll tell you about Valey separation and Valey filtering. So, some basics of graphene. As you know, graphene is made out of carbon atoms, identical carbon atoms, whose electrons in the valence shell occupy 2s and 2p orbitals in the isolated atom. When we bring two atoms close together, these orbitals hybridize, overlap and hybridize. In particular, the electrons occupying the 2s orbital and the 2px, 2pi orbitals hybridize to form the sigma bonds, which are represented by the straight lines in these lattice pictures. These sigma bonds are very strong, and so by that I mean that you require a lot of energy to deform or distort them, and are behind the strength that the material exhibits. And the last electron is residing in the 2pc orbital that, when it gets close to another pc orbital from a neighboring atom, forms the pi bonds. These electrons are occupying orbitals that are perpendicular to the graphene membrane, and they are the ones that are free to move around the material. From a theory point of view, the material is described by a perfect hexagonal lattice with lattice vectors A1 and A2. Each atom in the lattice is connected to three other neighboring atoms by the vectors, the next nearest neighbor or first nearest neighbors, vectors delta 1, delta 2, and delta 3, depicted here. And the two atoms in the graphene lattice are related by a mirror symmetry with respect to a plane that cuts the carbon-carbon bond by half. And because of, so if I put a mirror here, I reflect this atom, reflects perfectly on this one. Because of this relation, it's very customary, or is convenient to describe the two atoms or to label these two atoms with the letters A and B. So we will have electrons that come from pc orbitals originated in the green positions in the lattice, and we will have electrons originating or living in the pc orbitals coming from the B type of atoms. That's a usual description. So how this description is rendered in terms of a tie binding Hamiltonian? Well, for those of you that are a little rusty about the tie binding Hamiltonian, let me remind you that it's a way of writing the Hamiltonian in second quantization and in terms of fermionic operators. Here, the C and C daga are the fermionic operators that destroy the C operator destroys an electron inside J, while the C daga creates an electron inside I. So this Hamiltonian represents the kinetic energy of an electron moving in a lattice, jumping from site J to site I, and of course has to be made Hermitian conjugate. It has to have an Hermitian conjugate term to make the Hamiltonian Hermitian. In the case of graphene, these I and J sites are related by are connected via the vectors delta that I introduced in the previous slide, and this bracket below the sum represents the sum over nearest neighbors. Basically, there is only a short-range interaction, if you want, a short-range overlap between orbitals pc of different atoms. In graphene, if one atom if the electron is located in an atom of type A, let's say, then this connection connects the electrons in sublattice A with electrons in sublattice B. Now, the T parameter in front of the Hamiltonian is a measure of the strength of this overlap, or the easiness in which the electrons can jump from side to side, and it has a value estimated between 2.7 and 3 electron volts. Now, one way of describing the graphene lattice, hexagonal lattice, is using a Bravais lattice representation with 2 atoms per unit cell. An alternative way of describing it is to think about 2 triangular Bravais lattices, sublattice A and sublattice B. In both cases, we have the fermionic operator. We need the fermionic operator in the Taiwanese Hamiltonian to represent these 2 different sublattices, or these 2 different atoms in the unit cell. That means Ci can be representing electrons in pc orbitals living in sublattice A, or electrons in pc orbitals living in sublattice B. So we need to keep track all the time of these two objects to describe the dynamics of electrons in graphene. And that's why it is convenient to introduce a 2-component quantity that keeps track of this counting automatically for us. That's how the spinor is introduced as a 2-component object, like a vector, in which each component represents wave functions of electrons living in each type of atom. Now, this description is very intuitive because it allows us to think about a spatial term in this vector that describes the wave function of the electrons living in sublattice A, let's say, on atoms of type A. And to indicate that they are type A, we introduce the notation that we use for spin, although this is not real spin, okay? This is not a physical spin. This is a representation. And we could assign, for example, an arrow up, or the vector 1, 0, to represent the electrons that live in the atoms of type A. And we can use the opposite, the 0, 1, or the down representation for atoms that live in the atoms of sublattice B. Now, using this representation, the Hamiltonian then will have, the Taiwanese Hamiltonian will have the form of a 2-by-2 matrix, in which each matrix element can be obtained by sandwiching, or by taking the mean value of this Hamiltonian with respect to these new vector quantities, spinor quantities. Now, we do that. We express these space-dependent functions in a plane wave basis, or in a more intuitive way, we use a Fourier transform, or we think that we have free electrons, so we can decompose this in terms of plane waves, and we put that into the Hamiltonian. We do the sum over the nearest neighbors that I mentioned in a few slides before, and our 2-by-2 Hamiltonian has this expression here, where you see that, first of all, it's a emission, as it should be, and it depends on the momenta measured from the gamma point. Now, to find the energy as a function of the momentum, that is, to find the band structure of the material, we need to diagonalize this object, and it's easy to see that the diagonalization will give us the modulus of this quantity square, and if I plot the energy as a function of the momenta, what I obtain is the very well-known band structure of graphene. Here, the colors are meant to represent conduction band and valence band. Notice that the Fermi energy lies exactly at 0 at the neutrality point, which is a logical consequence of the fact that we have 1 free electron per lattice site, per atom in the lattice. Now, something peculiar about this band structure is that the valence and the conduction band touch each other at a number of discrete points. In particular, in this case, I drew 6 points, but there are 2 of them that are distinguishable. That means they are not connected by any reciprocal lattice vector, while the others can be connected with these 2 via reciprocal lattice vectors. These 2 particular points are known as the graphene valleys, and they are represented by the letters K and K prime. And what is even more interesting is that the dispersion around these 2 points is linear, which is very reminiscent to what happens when you study relativistic electrons, the Dirac equation. And when these electrons are massless, the Dirac dispersion becomes linear with a vertex that joins conduction and valence band. So if you see, I plotted a zoom in of these regions here that with the purpose to indicate that the physics, the dynamics of the electrons around these points seems to be quite independent of each other as long as I don't go to higher energies where this band structure obviously is not linear anymore. Now, what do I mean by low energy? Well, the measure of the low energy is when we compare processes that include energy exchanges that are much lower than the hopping matrix element that I introduced before. So if the hopping is of the order of 3 electron volts, well, I would consider a low energy process something, let's say, less than 1 electron volts in the hundreds of milli-electron volts, for instance, right? One more thing, notice that in this expression, which renders a full band structure, the momentum K is measured from the gamma point, and that's what I meant by this plot here. Now, it's since the physics at low energy can be, is dominated at what happens around these 2 K and K prime points, it's very convenient to expand this function F around these 2 points. Since I have 2 points, I will have 2 different expansions. So if I expand my K around the K and K, my little k around the K and K prime points, I introduce a new variable P, which is now measured with respect to these points. And the expression for my Hamiltonian now takes this form. It's now a 4x4 matrix because as I said, I have 2 expansions, one around K and the other around K prime. And now my spinor quantity will have 4 components that will be ordered in this particular way. If you notice the structure of this Hamiltonian is block diagonal, meaning that has upper and lower corners that are all zeros. So these 2 blocks don't mix, which is a way to represent the fact that the physics around these 2 cones are separated as long as we don't reach high energy processes. Now, in the expansion, my hopping parameter gets replaced, if you want, by an effective Fermi velocity, which is a measure of the dispersion in these 2 cones, and that has the value of 10 to the 6 meters per second. Now, each block in this block diagonal matrix can be written separately because they are not mixed, and that's how we introduce the Hamiltonian around K and around K prime that have these expressions. These are Dirac Hamiltonians for massless particles, that is, the mass is 0, and when we exploit the elegance of the Pauli matrices, these Hamiltonians can be written in a very nice form as indicated by these yellow boxes here. In this case, you see the wave functions, the spinor, sorry, are 2 components objects because we now are dealing with 2 by 2 objects here, and the order of these components are naturally given by the same order that I had in the original expression. So, one question is, well, I will have, if I want to describe electrons in graphene, I will have to keep track of these 2 Hamiltonians all the time. Is there a way that I don't need to do that? Is there a way that I can have these 2 Hamiltonians to look the same? And the answer is yes, I can do that using a particular representation known as the Valley symmetric representation. In this representation, I ask for the 2 Hamiltonian to look the same, but I have to pay a price for that. And the price is that I need to reorder the components of the spinor. It is, if you want, a basis reordering. In this case, the basis that I use around Valley K remains exactly as the one that I used before, but the basis that I use around Valley K prime has to change and acquires a phase factor in front of one of the components. In this regard, the easiness that we have to deal with only 1 Hamiltonian becomes a nuisance, a complication when I have to calculate any physical quantity in which I have to make mean values, to take mean values, because I need to remember what is a spinor in which I am doing this mean value. I am calculating this mean value. The wave functions, that is the expression of these objects in real space, take this form here, where the angle theta that describes the relative phase between these 2 components, that is, between the electron wave functions in the 2 sublattices, is the angle that is formed between the momentum of the electron and the direction x that I chose, remember, as the zigzag direction in the lattice. S here in front represents the sign of the energy, So this wave function can represent electron in the conduction and the valence band. And remember that momentum key is measured from K and K prime. Okay, so what happens when you include strain within this picture? Well, when you include strain, what you are doing is you are moving the ions from their equilibrium positions. In this picture, based on the lattice vectors delta 1, delta 2, delta 3, what you are doing is you are moving the atoms from their positions, so these vectors change from delta 1 to delta 1 prime, delta 2 to delta 2 prime, and so the same for delta 3. And they change by a displacement, so you are displacing the ions by displacement vectors that I wrote here as U for each of the three cases. Now, when you move the atoms, you may move them in the same direction but by a larger distance, or you can introduce also an angular change, right? You can move the atom from here to there. So in general, the modulus of the vector changes from the original length of the vector, and it requires a correction that if this modulus are changes are small because the displacements of the atoms are small, can be described with continuum elasticity theory in terms of the strain tensor. The strain tensor is, the components of the strain tensor are calculated from the displacement vectors, and the expression that I wrote here identifies displacement in plane or displacements out of plane with the letter H. So, because now the distance between the atoms is different, the tie-binding Hamiltonian will not have the same Hoping matrix element, the same Hoping coupling between any two sides, any two different sides. Now the Hoping will depend on which sides I am connecting. So that's why the Hoping acquires this IJ subindex. And because the Hoping, as I said, depends on, or it's parameterized with via the overlap of the two orbital wave functions, this overlap is measured in terms of an exponential function that depends on the distance between the two ions. So these new Hoping parameters can be replaced by this expression now. This coefficient beta it's a scalar, has a value of 3, and is related to the strength of the ion electron coupling or the phonon electron coupling in graphene. So, how do I introduce this modified Hoping in my tie binding? I explain it is by modifying the Hoping parameters. How does this strain appears when I do this expansion around the K and K prime point and work with the Dirac equation? Well, when I do the expansion, these T parameters, these Hoping parameters, the original Hoping parameter is now replaced by the new one, T prime. And what I notice when I do the expansion is that there are two combinations of these new Hoping terms that appear affecting the X and Y components of the momentum. These two combinations are written here and can be expressed in terms of the components of the strain tensor in this manner. Because again, I have two particular combinations that are independent of each other. If you notice, these are two antisymmetric combinations of the strain tensor. It's convenient to introduce what is known as the gauge field, a pseudo gauge field in particular, because this is how the Hoping term or the momentum is modified in the continuum limit. Now, doing the calculation carefully, what you notice is that the way that this combination enters when I do the expansion around the K point is with a plus sign, while this combination enters with a minus sign when I do the expansion around the K prime point. This is the look of these equations is very, very similar to the look that the Dirac equation has in the presence of an external magnetic field. The main difference here is that in the presence of an external magnetic field, the magnetic field enters with the gauge field that represents the magnetic field enters with the same sign at both valleys, while this particular gauge field enters with different sign. The fact that the gauge field changes sign when we move from one valley to the description from one valley to the description to the other valley is what makes this quantity to be a pseudo gauge field. It's a pseudo vector. In fancy terms, is the way that it transforms when I apply the mirror symmetry. It doesn't transform in the same way that the gauge vector transforms for a real magnetic field. Now, if this combination here, that is, if the elements of a strain tensor have a spatial dependence, that is, if they are inhomogeneous, I definitely can take the derivatives. Now, if the derivatives are such that I have a rotor different from zero, then I will have what is known as a pseudomagnetic field. And this pseudomagnetic field, because of its change in sign, will have different signs at each valley. Notice that not any spatial dependence on the strain tensor will produce a pseudomagnetic field, and not any spatial dependence will produce a constant pseudomagnetic field. Okay, so the strain has to be designed in very careful way in order to have a pseudomagnetic field and in order for this pseudomagnetic field to be constant or not. So, are these all the effects of deformation introduced? No, by no means. There are many, many other effects. The first one that I want to mention is that in addition to this change in the momentum via a gauge field, there is also the emergence of a scalar field that is proportional to the trace of a strain tensor. One intuitive way to see the origin of this strain field is to look at the unit cell in the lattice. If I stretch the lattice, I am moving the ions away, I am removing positive charge from the unit cell, and to keep charge neutrality, I need also to remove negative charge. So a condition of charge neutrality in the strain regions is the appearance of a scalar field, because this removal of electron charge can be thought of as applying a gate potential, that a negative gate potential that gets rid of the electrons in the regions when I have stretching. Now, this coupling constant that characterizes this particular scalar field has been estimated in different calculations. There is still a big controversy, but these days, most people are in agreement that takes a value of 2 or 3 electron volts with a negative sign. Now, what other effects have the deformation? Does the deformation produce? Well, when we change the positions of the carbon atoms, we are modifying the positions of the Dirac points. The expansion moves the Dirac points in the lattice, but for small deformation, the motion of these Dirac points is very little. They don't move very far apart as long as the strain is small, and as a consequence does not affect the emergence of these pseudomagnetic fields, as long as we can think about the valleys as being separated, not overlapping. So these terms are not important unless you are in the regime where the two valleys talk to each other. Now, another effect is that when we have the membrane that is curved, these pi orbitals are no longer that are always perpendicular to the membrane. When the membrane is not flat, when the membrane is curved, these pi orbitals also tilt away from each other, changing the overlap. This can also be expressed in terms of another pseudo vector field that has this expression, and as you see, it depends on higher order derivatives of the deformation that produces the curvature. The strain also renormalizes the Fermi velocity, making the Fermi velocity anisotropic if the strain is anisotropic. Now, changes in the Fermi velocity in the description of the physics also enters with terms that are linear with the strain, and because they come multiplying the gauge field, the terms that give rise are higher order in the strain. So what I'm saying is that in the description of the Dirac Hamiltonian, I will have BF times the gauge field, and this will be terms in higher order. One systematic way to obtain all the possible terms in the continuum description in the Dirac equation that are introduced by this change in the in the lattice vectors, in the first neighbor lattice vectors delta, a systematic way is to be guided by symmetries. So using the symmetries that are allowed by the graphene lattice, so we can keep talking about graphene as material, the low energy derivation in a systematic way can be obtained by taking these symmetry considerations into account. And this has been done in the past, and at the end, when I mention the references, I will direct you to that particular work. So the summary of this first part, basically to conclude this first part, which is a review, the points that I think it's important for you to remember is that in the low energy regime, the physics of graphene electrons is characterized by two particular points, it occurs around two particular points, the K and K prime valleys. The dynamics of these electrons is described by the massless Dirac equation. And it's useful to keep track of the electrons in terms of a quantity that is a pseudo-spin, that is a two-component vector-like object in which each component represents what happens with electrons living in each type of atom in the lattice, where these two atoms are related by reflection symmetry. Finally, the effect of a strain is to introduce a main effect that I am going to focus in the rest of the tutorial is that it introduces a pseudo-magnetic field that is caused by the deformation in these first neighbor lattice vectors, and this pseudo-magnetic field is represented by a gauge field that enters with different signs at each valley. Okay, here we are going to start with the second part of the tutorial, in which I am going to show you how these strain fields modify the electron, the charge distribution, and the electron dynamics. So let's start. Share the screen. And here we go. So as an example, I decided to focus on a particular deformation that appears very commonly on graphene samples. When graphene is deposited on a substrate for different reasons, lattice mismatch, temperature, chemical treatment of the materials, makes possible the appearance or the emergence of wrinkles and folds. A fold is a deformation that appears as an out-of-plane deformation where the material bends and separates from the substrate. And as an example, I am going to focus on a Gaussian fold. Gaussian simply because the mathematics is simpler. In this case, I have a fold shown like this in the upper corner. And along the axis of the fold, I would expect translation invariance, because nothing happens there, but across the fold, I see a Gaussian shape that is described by this formula over here. The maximum height of the fold is given by this height, h0, and the width at half height, the width is determined by this parameter v. So changing these two parameters, I change the geometry of the fold. For simplicity also, I decide to choose the orientation of the fold along the zigzag crystalline direction. In that way, my fold, the axis of the fold, or the translation invariance, occurs along what I call the x direction. When I calculate the strain tensor coming from this particular deformation, what I find is that the strain tensor gives rise to a gauge field that only has one component, ax, that in this geometry, that depends on y. So the only component of the gauge field changes along the direction going across the fold. Now, because this is a Gaussian shape, I will have many derivatives. At the end of the day, I can calculate the pseudo-magnetic field, and I will see that the pseudo-magnetic field has a profile as described in this figure. The pseudo-magnetic field shows translation invariance along the fold axis, and across the fold, it goes alternating in sign. Remember that the pseudo-magnetic field is calculated at each Dirac point. So to visualize the profile at the different Dirac point, you just have to invert the color scale. And you see that the magnetic field goes from negative to positive, and so on, oscillating in the fold region. Now, if I draw a cut of this profile, and I plot it here as with a red color, you see that the pseudo-magnetic field has a very variable shape with valleys and barriers when I go across the fold. At the same time, the gauge potential, the vector A, which has only one component, the only one component, has the structure of a double barrier. So I said, well, a double barrier, I know how to deal with double barrier problems in quantum mechanics. How does my Hamiltonian looks like, my Dirac Hamiltonian looks like in this case? Well, I go back to the equation for the Hamiltonian, and I see that using the Valley symmetric representation, I see that the kinetic part looks the same for both K and K prime, but my A field, the gauge field, the AX component, is affecting the momentum along the fold axis, okay, along the translational invariant direction, and changes sign as it should when I go from one valley to the other. Again, here is a profile of the strain field or the AX component, which in this case are the same, and the profile of the magnetic field. So, because this profile corresponds to a double barrier, let me return a little bit to emphasize, this will translate when I replace the P operators by derivatives and I apply on the wave functions that have plane wave solutions, right? I will get a differential equation, and that's how I will solve the problem. This profile as a two double barrier is a little bit more complicated than having one barrier. So let's play with a one barrier problem first. So in the one barrier situation, I have my gauge field that acts at the barrier within the region between Y2 and Y1. This is roughly B. And I will propose wave functions that will exist in region 1 and 3 and in region 2, and I will match the boundary conditions accordingly, exactly in the same way that we solve problems in quantum mechanics. So I will look first for solutions that are extended waves in all 2 dimensions. Extended wave in 2 dimensions means I will have plane waves in the x direction, both in regions 1 and 3, where there is no barrier, and in region 2, because of the translation invariance along x. And along y, I will also propose plane wave solutions in 1 and 3, where I don't have any barrier, so I have free electrons. And in region 2, I will have a momentum that I will look for to have real values there, so I can have also a plane wave in this region. And I will propose this as solution to my differential equation, and I will find what are the solutions that I have for this momenta and at what energies. Here I wrote down the explicit expression of the momenta inside the barrier, and you see that the relation between the momenta inside and outside the barrier should satisfy the energy momentum relation of the Dirac equation, that is the linear relation between the energy and the momentum. In the case of the free regions, the momentum along the 2 directions will depend on the angle of incidence with respect to the axis of the fold. Inside the region, the momentum along y is the one that will be modified in terms of the modification that the momentum along x has, because the momentum along x will be different from the momentum outside the barrier due to the presence precisely of the barrier. A similar scheme can be done for momentum k prime, except one changes the sign of A. So, what is the top view of this situation? Just to clarify ideas. Well, if you see, I have here an electron in black incident from the valley K, in which I use the decomposition in components X and Y to indicate Kx should be the same in both sides of the fold, here and there. I have the same Kx component, and the Ky component will be the same here and here. It's exactly as in optics. And inside the barrier, my momenta will be modified following these 2 relations. I, again, as emphasized, the change in sign in A due to the fact that the strain produces a gauge field that changes sign. So I calculate transmission, as I do in quantum mechanics. I calculate the transmission and the reflection coefficients, and I plot here the transmission for states with energy E and different incident angle theta for the problem of the single barrier. And you see that the color scale indicates red, transmission equal to 1, blue, transmission 0, and the angle is measured with respect to the 6-an orientation. An angle of 0 is parallel to the fold, going left to right, say. An angle pi, which is this one here, is going right to left, parallel to the axis of the fold. And you see that for a wide range of angles, I have zero transmission coming from states, 4 states coming from valley k, while I have, let's say, between 0 and pi over 3 or pi over 4, I have transmission equal to 1 for a wide number of states at different energies. While I am parallel, when I am looking at the incident completely parallel to the axis of the fold, I see that I have transmission through discrete points, discrete values of energies, which corresponds to resonances. This is what I naturally correspond. The same happens when I am incident in the opposite direction, also parallel to the fold, but in the opposite direction, let's say right to left. I have resonances, but this time these resonances are only for states coming from valley k. So as my states are incident in the fold area closer to be parallel to the direction of the fold, I will have transmission from one valley more than from the other. That's what these plots are telling me. This is a single barrier. What happens with a double barrier? Well, we all are familiar, hopefully, with what happens when you add barriers in the transmission problems, and the addition of barriers, what they do is they split the resonances, and that's what we are observing here for valley k and k prime, and also we see the emergence of other resonances that are related to the existence of the gap between the barriers, of this well that is formed between the barriers. Now, these solutions that I just showed you correspond to extended states all over the two-dimensional plane. So I will have extended waves in X and Y. I could ask also if there are solutions that exist only within the barrier region. In this language, that means the relation between the two components of the momenta in regions 1 and 3 is given by the relation via its modulus that is fixed by the energy. So if I fix the energy, I fix the modulus, and I could ask, could I have solutions in which one of the components is greater than the modulus? If there are such solutions, then the momentum along ky would be imaginary, which will mean that in regions 1 and 3, I will have evanescent waves living in the barrier region, but going to 0, decaying towards the region outside the fold. So the solutions that I will propose for regions 1 and 3 will be of this sort, where you see the plane wave along X, which is the translation invariant direction, and evanescent waves as I move away from the fold. And I look for the solutions, and not big surprise, I find them. In these plots, I am plotting energy versus the momentum along the fold, because I want to show the band structure of the dispersion of the states that appear within this barrier, this fold area. So red again indicates transmission 1, blue indicates transmission 0, and this region, the red region, corresponds to the solutions that I have found previously, where the states are completely extended. They exist both in the region of the fold and outside the region, in the region of the barrier and outside the region of the barrier, but in both cases, they are extended waves, plane waves. However, what I find is that for certain values of the momentum along the fold, I find states at discrete energies, where these states have a very well-defined energy-momentum relation, that is, these states are dispersive, and they appear at the energies in which the resonances that I found for extended waves appear in the first case. So this plot shows that these states appear for both K and K prime valley in identical fashion. When I put two barriers, these resonances that were split, extended resonances that in the extended solution, well, when I put the two barriers and I look for evanescent waves, I find that these evanescent waves also split and more states appear, more bands appear. Okay. I remember these states, these bands, refer to states that live in this area and that die away outside the barrier area. If I want to ask, okay, well, I found evanescent states that exist only within the barriers, meaning where the fold is, where the deformation is. How are the wave functions, or what do the wave functions look like? Well, for this model, it's very straightforward to calculate wave functions. So I am here plotting the wave function of a state that is very near the zero dispersion, very close to zero energy, here marked by the square, black square, and I look at the wave functions, and remember that all this formalism is using spinors in which I calculate simultaneously the wave function for electrons living in sublattice A and electrons living in sublattice B. And what I find is that the wave function has a two-peak structure. One peak is located at one border of the barrier, at one edge of the barrier, and the other peak is located at the other border of the barrier. And one peak corresponds to electrons that live in sublattice A, while the other peak corresponds to electrons that live in sublattice B. Because in this area, the barrier changes, the A barrier changes so abruptly, the magnetic field here is effectively infinity. The magnetic field is the derivative, right? And an infinite magnetic field will tell me that these states most likely correspond to Landau level. And this is consistent with the fact that the band here, they belong to a band that seems to flatten, like I would expect from a Landau level. What happens with a state that is dispersive here? Where does this state live? Well, this state, the wave function corresponding to this state, is also a two-peak structure, in this case a four-peak structure, in which I can see that the peaks for exist inside the barrier. They have a sinusoidal component, an oscillatory component, but they exist inside the barrier, and effectively they decay outside the barrier. And again, if I look at per component, that is per sublattice, I see that the states are distributed in each sublattice and slightly separated, the maxima separated slightly from each other. So these states are separated per sublattice too. What happens? So this intuition that I gained from solving a square barrier problem and a double square barrier problem is very useful in the interpretation of the results when you take a more realistic viewpoint. A more realistic is a fold like the one that we solved before, in which, let's say, we choose a Gaussian profile. In this case, we calculate using a tie-binding model. The intuition came, remember, from solving a Dirac Hamiltonian. In this case, we want to calculate it in the lattice, and we use a tie-binding model. So we propose a profile for the deformation, and we use this profile that tells me what is the position of the atoms in this ribbon. I use this profile to calculate the strain tensors. With the strain tensors, I calculate the new nearest neighbor lattice vectors, delta, and I use this delta to find the modified expression for the Hopin matrix elements. So basically what I am doing is I am implementing a tie-binding Hamiltonian in the lattice numerically with these new Hopin terms that change between that change for each pair of atoms that I consider. I solve this Hamiltonian and I find the band structure, which is shown in a little insert here. This is for valley K and for valley K prime. And I decided to illustrate the probability density, that is the square of the wave functions, for two particular states. Let's look at the states signal at this point, this energy and this momenta with red in valley K and in valley K prime. I chose states that have the same group velocity, that is, they are moving in the same direction. And what I see is that states with the same group velocity in valley K are centered in the region of the deformation. These are the red curves here, while they are centered outside the deformation if they are coming from K prime. So if I look at states with the same group velocity, I will find the states from valley K at the center and the states from valley K prime in the outside of the deformation. And the same happens when I choose group velocities that are negative, which is the case for the blue points. Here you will see that the states are also differentiated, the wave functions are differentiated per sublattice, and the sublattice, as we saw before, in the square barrier problem, they are slightly, the maximum amplitudes of the wave functions are slightly separated too. This plot here summarizes these results in general for the probability density, where the color scale, as a function of the position, where the color scale tells me which states come from valley K, which is the yellow, and which state comes from valley K prime, which is the black. You see that in the center, I have mostly yellow color, so in the center, I will have the states with valley K, and in the outside, I will have the states with valley K prime. So basically, if I send a current through this fold, my current will be separated by valleys spatially. There will be a spatial separation of the current with the states coming from one valley localized more on the center of the fold and the states coming from the other valley in the outskirts of the fold. These results hold if the fold has a shape that is not Gaussian, but respects the reflection symmetry with respect to the center, and also hold for the shapes that are asymmetric, of course, with the corresponding variations in the dispersion of the states, and the energies in which you can find the states. Notice that in all cases, when I have a large magnetic field, I will have a better defined flat band, and the states will separate or will accommodate if I have a larger barrier geometry, as expected from the simple geometry problem. So, one question that you may be asking is, what is the difference between these confined states and the pseudo-Landau levels? In that sense, let me remind you a little bit about the physics of the pseudo-Landau levels. We talk about Landau levels when we have an homogeneous magnetic field distribution. In this case, it will mean to have a strain distribution that generates a gauge field such that when I calculate the curl of the field, I have a constant. That is a gauge field that changes linearly with the position. This is quite a challenge to design experimentally, but in principle, it's possible, and there have been many, many proposals in the literature. The consequences of a homogeneous magnetic field, or this type of strain, is that the states in the density of states get bunched in a series of peaks or bands that are separated from each other following a dependence on the magnetic field that goes with the square root. So we say normally that the scaling of the energy levels goes with the square root of the magnetic field. In typical STM measurements of the density of states of graphene samples, this effect is observed by a number of oscillations in the DIDV, which is a measure of the density of states, in the DIDV signature as a function of the sample bias, as presented here, and the separation of these oscillations is, one looks to see if this separation follows a square root law with a magnetic field, or is linear with the square root of the magnetic field. Theoretically, the magnetic field is implemented in the tie binding via what is known as the Pilot substitution, a flux per unit cell, and in the continuum limit is introduced, as we said in the first part, as a gauge field that is has the same sign for both valleys. Now, what happens with these confined states that are due to magnetic barriers, that is, to an inhomogeneous magnetic field? The exercise of the single and the double barrier that we saw before tells us that there will be, in the presence of a varying magnetic field or a barrier type profile for gauge fields, not linear, but with a more complex geometry, it tells us that there will be transmission through the barrier when the height of the barrier times the width, when the momentum of the wave and the width of the barrier are an integer number of factors of pi. So basically in those cases, the dephasing produced by the presence of the barrier will produce constructive interference and will have transmission. When we have two barriers, we have a similar situation, the transmission through each barrier, but we will have new resonances in the well region, which are this bound state. Now, the resonances inside the well region will depend on the height of the barriers, which is given by the maximum value of A0, and the width of the barrier. Now, the height of the barrier is given by the strain that in these models goes with the height of the fall divided by the width of the fall square. The strain is measured by this coefficient eta. So the height of the barrier goes like eta square. And the width of the barrier is basically the region where the fall exists, which is roughly B to B, proportional to B. The states that appear inside the well are dependent on the height of the barrier and the width in this particular relation and in a potential well structure. But this particular relation happens to be the maximum value that the magnetic field, the pseudo-magnetic field takes. So we see that the level spacing between the states that appear inside this double barrier region will follow a linear scaling with the magnetic field, in contrast to the square root scaling observed for Landau levels. So when one takes a look at the measurements of density of states, DIDV in STM features, for instance, or when one measures variations in the density of state, this scaling is a clear signature that the strain distribution is such that does not produce a homogeneous magnetic field. And we are not talking about Landau levels, but states confined by magnetic barriers. So the summary of this second part is that a simple strain geometry that we went over, in this case the fall, shows that strain regions are able to confine charges. So they produce a charge redistribution with the charges accommodating within the strain region. Along the strain region, in this case along the fall, we see that there are states that disperse along the fall that live inside. So we have waveguiding behavior. Moreover, we see that this current is composed by currents coming from the two valleys, which are located in different spatial regions. That is, there is a spatially valid polarized current, the one that is conducting through these faults. And by looking at different variations in the geometry, we see that these results are relatively robust. One signature of the presence of these states in measurements of local density of states is its scaling with the maximum value of the magnetic field produced by the strain. And here we are with the last part of the tutorial, in which we are going to see how these ideas can be applied for potential device applications. So can we exploit these features for applications? So the idea here would be to expand in a realistic way the application of Valley currents to the topic of Valleytronics. So basically is to consider the information that the states come from one particular valley or the other in the graphene band structure in the same way that we use the electron spin, with spin up and spin down used as carriers of information. In order to do that, we will need to know how much of this valley polarization and this valley separation persists if we have states that are not necessarily running along the fall, but they are incident at different angles with respect to the fall. And if the fall can really be used as a beam splitter in the similar way that optical beam splitters are used in optics. So we took our Gaussian fold and we implemented the continuum model for it, and we used the scattering matrix method to calculate what are the transmission coefficients for states coming from valleys K and K prime for different energies and with different angles of incidence. And this is what this plot shows here. The color code represents red transmission equal to 1, and blue transmission equal to 0 for states that are incident, impinging on the fall on one side, and we are looking at what remains of these states on the other side. And we see that for a quite wide range of angular incidence, we have practically no transmission for states coming from one valley, while we have resonant transmission at particularly at directions parallel to the axis, but going away from the axis of the fall, we have transmission by a quite number of states coming from valley K prime. Meaning that if we are with an angle of incidence, let's say of 15, 20, 30 degrees, we will see all the states on the other side of the fold as being emerging from Valley K prime, as being originated from Valley K prime with no Valley K states present in that current beam. Now, in order to see how strong this polarization is, we look at how the polarization changes as we change the angle of incidence, and we use this coefficient P that is defined as the difference between the transmissions coming from states at different valleys divided the average transmission, and we plot this polarization in this color scale. Again, 1 is maximum polarization, that means the transmission from valley K prime is 0, -1 means the transmission from valley K is 0. And as a function of the different angle of incidence. And except for pi/2, that is for incidence perpendicular to the fold in which both valleys go through, we see a wide range of angles and energies in which the currents, the transmitted currents, are really very well polarized. Now, we are confident that the polarization is an effect that exists. The question is, will we be able to measure it? Because in order to measure these polarized currents, we need to have a current. And what happens is that we not only need to know how polarized the current is, but we also need to know how strong this signal is, how much amplitude we have there, how much current we have there. In order to do that, we calculate the product of the transmission coefficient times the polarization, because that tells us how much signal do we have and how polarized the signal is. And then once again, we do this for states from valley K, and we see that for incidence above 90 degrees to anti-parallel to the axis, we have a large grade of polarization for states coming from valley K and a completely absence of states from valley K prime. So this is telling us that for a wide range of angular incidence, the folds are very good valley polarizers. In the same way, we change the strain intensity, and we find for different strain intensities that are realistic according to folds and wrinkles found naturally in graphene samples these days. And for a wide range of angles, we find, again, high transmissions and valley polarizations. So this again, is the valley polarization times the transmission for different values. So the summary of this last part, the things that you are strongly suggested to remember is that graphene folds are very good valley beam splitters, and that the valley polarization that they produce is quite robust against variation of in the geometry and the energy. And with this, I finalize the tutorial. If you would like to know more about connections of these results to experiments, I invite you to listen to my talk on Monday. One caveat: as you may notice, I have not included any reference in the tutorial. The main reason is that the topics that I touched upon have been the subject of many publications and works and presentations and tutorials and works online, presentations online, which would have been impossible to cover, and I would have required tons of more slides. So what I decided was instead to refer you for more details and the most relevant references to a brief review that we wrote a couple of years ago. At the time, we were very careful with the references. You will find tons of reference to different works. And if there is any topic in particular that you would be more interested in learning, please contact me. Okay, thank you very much for your attention.